Good afternoon, everyone, and thank you for being here today. I need to read my review, so I sit here to have my talk. And then today I will present two interrelative contribution in the robotic, in the robotic. Then the RoboBrain is a unified is an VLM model that is a brain model of the for the robotic manipulation, and RoboOS is a hierarchical, calibrative, and frameworks that connects the brain model and the robo agents, the celebrate model. Then my name is I'm Minglan from the BAI, and I'm an embodied intelligence researcher. Okay, let's begin with the chance of the AI. With the since the emergence of the ChatGPT, we have transitioned from the AI 1.0, mostly small models, into the AI 2.0. Most of our models is a large model. Then in this during this period, we've seen many an explosion of innovation. Like the large language model, video language model like GPT-4b, and even video generation model like Sora and Kelin from the China, and in the okay, and as we stand at the threshold of the third grade of AI, I think the embodied AI will be the next GPT moment. And now, okay, please. And I think the embodied AI will become the main force of the AI technology development over the next decades, and it will lead into new revolutionary production and reshaping the instruction landscape. And then let's take a closer look of the chance of the embodied intelligence. I have categorized the reason process along there the three dimension: task, ontology, and the scenario. Before the 2023 and earlier, we most of our model just has the capability of to deal with single task, single ontology, and single scenario. But after the 2020, but by 2024, many models have the understanding and task decision making capacity. And with the large model and the big data with scaling law, we get the general intelligence systems which can handle with the multiple ontology and multiple scenario. Then here's the milestone in the embodied intelligence, and the content in red colors is from our BAI, and here's the RoboMember, Lift 3D, and RoboBrain. RoboBrain is a VLM model just for the robotic manipulation, and hybrid VLA is a VLA model for the cerebral agents. For the several agents, and the RoboOS is a framework to connect this RoboBrain and the VLA model. So here's the pathway to to embodied intelligence. There are two major technical approach. The first one is end-to-end vision language action model, such as OpenVLA Pi0 and RT0 GR0. This model aims to directly map the visual and the text input to motor actions. and through the large multimodal large multimodal architecture. And then the second part is the brain cerebral collaborative frameworks. The RoboOS from BAAI and Alex Gemini Robotics recaps and so on and so on. And this architecture promotes modularity, scalability, and real-time responsiveness. Okay. Then here's a question: Why we choose a brain cerebral collaborative frameworks? Then we all know that the most of our end-to-end models has a strong capability of the decision making, but they also suffer from the limited generalization and scalability due to the constraints in environment interaction and hardware adaptation. Yeah, and in contrast, the framework that has a strong generalization and interpretability. The three key points we concerned is that the modularization, generalization, and interpretability. Then the brain cerebral collaborative frameworks represent a simpler and more effective approach to realize the embodied intelligence. Now, building on the discussion before, now we turn our attention to the main part of the framework, the brain itself, I will bring the RoboBrain, unified brain model. Okay. Then here's also a question. Can traditional VLM serve as the brain? What's the difference between the traditional VLMs and with our robotic model? The main difference is that the traditional model is facing the challenge, particularly in the long horizon of operational capability. Here's two examples. On the left image, we give the yellow trajectory lines to the GPT-4 and ask it what will happen next. Then unfortunately is misunderstanding the trajectory. And in the left side, we give a task to the RoboBrain, putting the pot in the river. We give the RoboBrain not only provides a detailed response, but also outlines a series of the steps. Okay. Then. To effectively perform the long horizon operation tasks. Here, our robotic brain must process these three capability. First of all, task planning capability. It means that the model should transfer the abstract instruction from human into a sequence of executable subtasks. The subtasks will give to the agents, and the agents will understand it and to do any. Okay, here's an example. The task is to leave a teapot and pour water into a cup. And the RoboBrain or the brain model will give the step 1, 2, 3 to which the VLA model, cerebral model can understand. And the second part is the affordance perceptive capability. Most of our models should have should identify the operation region of the objects, like the the part of the cup to for the agent for the arm for the robot arm to grasp, and then the thirdly. Trajectory perception, trajectory prediction capability. Our model needs to predict the motion trajectory from the origin position to the target's position, and which guides the robot arm to get the correct thing, the correct object. Okay, one of the main reasons why existing VLM model can struggle in embodied scenarios is that the lack of the high quality training data sets. We created 50,000 high quality episodes from the open source data sets, OpenX embodiment, and some come from the internet data. The shared robots data set is is highly diverse and covering the high-level task planning, object affordance region, and effect trajectories. Okay, based on with the shareable data set and the internet data about like image, video, and interleaved content, we change our RoboBrain. Okay, the RoboBrain serves as a critical bridge, translating the abstract human instruction into concrete, executable robo actions. Okay, during inference, the RoboBrain will first process the visual inputs like image or video and the human instruction in text into a sequence a series of executable subtasks. A subtask is also a short task test. And then maybe sometimes you will, if needs, it will perform the affordance and trajectory part of the with different subtasks. And here's our model architecture diagram. We use the SIGLIT as the visual model and QWin 2.5 as the LLM module. Okay. Here's our training strategy and the data. We split the whole training procedure into two phases. The first one will for the general object visual grounding training, which can we input some object name or some description, and the model will output a square to point out the objects in the image. And the phase two for the robotic training is using the robotic data for the manipulation, affordance, trajectory, and any understanding from the view of the robot. Yeah. You can see the stage 1.5 and stage 2. We use the caption data set. The caption data set is an image with descriptions and image and multi image and video in the phase 1, and in phase 2 we use the robotic data like the step just now the step 1, 2, 3, and affordance trajectory. Yeah. Here's the experimental results. After the training, all the 4 training stage, our RoboBrain outperformed all the baseline model across these 3 embodied task for planning. Yeah. And the baseline model is Lava 1.9 Class 3 GPT-4V. Yeah. Okay. And then here's the performance in operable region perception and trajectory prediction task. We keep the similar capability of the general multimodal, and then we get a better improvement in the affordance and trajectory capability. Yeah. Here's the visualization of the task planning. Once we give the task to the model, and it can give the multi-step response. And here's the case of affordance. We give the task gene with the cup, and it will output a square to point out where for the robot's arms to grasp. And here's the trajectory case. Once we give a task, make a piece of toast with the oven, and here the line will guide the robot arms to move. Okay. And the official CVPR review on embodied intelligent chains reference our robot brains in the first page. Yeah. Okay, over there. Then we just talked about the RoboBrain, the high level reasoning part of the RoboOS, and then the whole RoboOS is a hierarchical framework. Then framework. You can talk about that. Is a cross ontology embodied brain celebration frameworks. Here are the RoboOS consists of 3 key components. The first part is that the embodied brain model, just we talked about, and then the second part is the Celebrate Skill library. Designed with a modular plug-and-play approach to enable seamless execution of diverse skills, including navigation, manipulation, and customization tools. You can see that the navigation capability, manipulation capability, and even the whole body control capability, like the dancing or dancing with the G1. And then altogether, and then the third one is that the real-time shared memory system is a spatial and temporal memory mechanism that facilitates the coordinations and scheduling amongst multiple agents. Yeah. At the same time, the shared memory enables efficient multi-agents collaboration, paving the ways for scalable intelligence system. Okay. Let's talk about here's the okay. At the core of RoboX lies RoboBrain. The RoboBrain names slow system. Here are three key key points of it. Firstly, spatial temporal perception. Yeah, we should. Okay. RoboBrain feels the RoboBrain will have the capability of the state checking for the dynamic spatial temporal cognition, and they also have to get a very perfect planning guides for the next VLA model, and on the third part is the feedback and the error correction. Once we transfer the task to the subtask and the subtask to action list for the VLA model. Once the VLA model makes some mistakes, it will give a feedback to the prior level. The prior level will give a replanning, and then give a new task a new action to them. The second part is the Celebrance skill library. It's a fast system. Yeah. This system this system has a skill. Wait a moment. This system has a plug and play. Plug and play skills, which means that you can use our RoboOS frameworks. You just need to prepare your manipulation skill functions, like the anygraph or the VLA model of your own. And then you can fix all kinds of the agents. Yeah. Then it's the same with the navigation skill. You can prepare your SLAM or VLM models, and then we can with the capability with specific tools for different embodiments. It also can be used in our frameworks. Okay, and yeah, here's the third capability of our frameworks is the shared memory system. It is a close ontologies multi-robot data hub. The first one of its key components is the spatial memory. It can real-time updates of the object spatial relationships. The first time we go to a new environment, we can scan the room and split all the objects into a profile. Here each object has its name and ID and the spatial relationship with each other, and here it also has the temporal memories, which keeps a detailed. It will keep detailed logs of past action and task execution states. This the stat, yeah, and the ontological memory will record the information about all robots in the system in the framework. And once the robot is missing or has or in an error state, the RoboBrain will assign a new one to replace it or get feedbacks. The RoboOS here's a RoboOS built on our flex scale frameworks, which can namely support the edge and the edge cloud collaboration for the multi robot system, and it will be very fast and provides a memory optimized data access and engine. Okay. When you if you want to use our RoboOS frameworks, you can get a customized fine-tuned data sets. Here's an example. The task I want to eat fruit. At the beginning, the model should give a reasoning, analyze the fruit location and the robot stats based on the shared memory, and then it can predict which robot to do something. For example, robot 1 to retrieve the fruit bucket to the kitchen, and then robot 2 as a chef can place the pear and the fruit knives into the buckets, and then the robot 1 returns with the basket, and then and the second part is the subtask to the tool, which the tool is a function that the robot agents can understand and can execute. Yeah. The subtask is retrieve the fruit basket to kitchen, and we can get the navigate to serving table and grasp the basket and navigate to the kitchen table. Yeah. When fine tuning the RoboBrain and your VLM model, we can first use the COTSFT to change the to make the model have the reasoning capacity, and in the next phrase, we use reinforcement learning like R1, GRPO to train the model and make it to exactly outcome function. Yeah. Here's a demo. A demo. I want to eat some fruits, and then wait, sorry. It means please help me to put the apple closest to the cup into basket, and then give me a fruit knife. That's the affordance. Take a photo and recognize the capable parts of the object of the knife. Okay, here's our open source links of the RoboBrain, RoboOS, and the reason FT. The reason FT is the how to change the VLM model to fit the RoboOS. Yeah, maybe you should take a photo. Okay. and welcome to our booth in the in this position. Okay, that's all. Thank you.